Today we'll work a little bit more with buffers, and there are two ways that you can make a buffer. The first is by directly mixing a weak acid with its conjugate base. So as an example of that, if I would choose the weak acid acetic acid, so C2H3O2, you should remember that the conjugate base of this acid is C2H3O2 minus. If you don't remember that, go back and look at Module 7 again. So this is the conjugate base. When you go to the laboratory shelf, you're not going to find just ions. You don't find chemicals that way. But what you could find is a salt that contains this ion. So it might be sodium acetate or potassium acetate or any number of other acetates. And so what happens is that when you put this into solution, this will completely dissociate, giving you sodium ions and acetate ions. And so then this acetate ion will be the conjugate base of this particular weak acid. The sodium ions will just be hanging out in solution. They're not really going to react with anything, unless, assuming you don't put anything else too crazy in there. And so there you've got your weak acid and its conjugate base. So I can put these two things together to make a buffer system. The other thing that you can do is you can mix a weak acid with a strong base. Now I know that initially probably sounds a little funny, because how is that going to work? Because it's supposed to be a weak acid and its conjugate. Well, let me explain to you how that works. So if you take a weak acid, and we'll use the same one, but this time I'm going to mix it with a strong base. And let's use sodium hydroxide, okay? Whenever I have a reaction with a strong base or a strong acid, they are going to go to completion for all practical purposes, okay? So if you remember solving these types of equations before, these dissociate in water, this hydrogen goes with this hydroxide, and so I end up with water, and then I'm gonna have sodium ions, and I'm going to have acetate ions. Now, I have my weak acid and my conjugate base as long as one thing is true. As long as I use less of this than what I have of this, so that this is my limiting reagent, and I'm going to have some leftover I'm going to have some leftover weak acid. Then, as long as I have some of this left over, this is all used up, then I will have weak acid and its conjugate base set up, and then voila, I have a buffer system. So this technique works as long as you're careful to use a stoichiometrically lesser amount of the strong base than you have of the acid. Now, we can calculate the pH of a buffer system based on the Henderson-Hasselbalch equation. And that equation just says that the pH is going to be equal to the pKa plus the log of the concentration of the base over the concentration of the acid. pKa, again, as you've probably read in your book, you know that pH is the negative log of the concentration of hydrogen ions. The pKa is the negative log of the Ka, which is the acid dissociation constant. Okay, so if the acid dissociation constant for this is 1.8 times 10 to the minus 5, as long as I take the negative log of that, I'm going to plug that in and it will be the pKa. Okay, so nothing, it's not a new concept. We're just applying the concept of pH to the Ka so that I will end up with a pKa. While this equation may look very complicated right now, by the time we get to the end of this chapter, you won't even need an index card to remember this one, because you'll know it like the back of your hand because you've used it so much. So let's do a couple of example problems so that you will understand how to use this equation. And once I get to the end of the first example, I'm going to point out a couple of principles that you probably are going to want to write down, because the project that I have you working on, as well as, who knows, maybe some exam questions, may hinge on a couple of these concepts, and he doesn't particularly point them out in the book, so I want you to make sure that you have got those written down when we get to that here in just a second. We're not going to get through this entire section today. I'm going to get through the first couple of examples, let you practice those a little bit before we go on and finish the section. So we're going to look first at example 8.1, and example 8.1 says that a buffer is made by taking 100 milliliters of 10 molar cyanic acid and mixing it with 100 grams of potassium cyanate. The resulting solution is then diluted with distilled water to a volume of 1 liter. We want to know what the pH is, and they give us the Ka. So if I'm asked for the pH, I have to know, first of all, that I have a buffer system. And if you look at the two chemicals that they gave you, you've got HCNO, which is a weak acid, just because it's not one of those that you memorize as being a strong acid. KCNO is going to dissociate in potassium ions and cyanate ions. So therefore, I have a weak acid and its conjugate base. So therefore, I'll be able to use the Henderson-Hasselbalch equation to figure out what the pH of this solution is. But in order to use that, I have to find a couple of things first. So let's get the equation up here. pH equals pKa plus the log of the concentration of the base over the concentration of the acid. Okay, so let's start with HCNO. It says that I have 100 milliliters of 10 molar. So if I have 100 milliliters, that's going to be 0.100 liters times 10 molar. And so that then is going to give me a concentration, or it's going to give me, not a concentration, it's going to give me a number of moles of 1.00 moles. Okay. Then, because this is asking for concentration, I can't use moles, I've got to use concentration. So I've got to take that back and figure out exactly what the concentration of it is. So because I have, it tells me that they're going to dilute it to a volume of 1 liter, I'm going to have 1 mole in 1 liter of solution, and therefore my concentration is 1 molar. I do want to point out something. Hopefully by the time you're in advanced chemistry, you know this already, but I have so many students that do this. I have students who want to go 1 mole, it's diluted to 1 liter. I can do that in my head. I don't have to write it out. But what they tend to do is they tend to want to put an equal sign in here. 1 mole and 1 molar are not equal to each other, because if I diluted this to just 500 milliliters, then my concentration would be 2 molar in place of 1 molar. So please don't make the mistake of stringing equal signs along, because moles and molarity are not equal to each other. That's why I wrote the arrow there. Whether that's the technically correct way to do it, I'm not entirely sure, but I do know that we don't want an equal sign in here, because these two things are not equal to each other. So please don't just string your equal signs along if you have things that actually aren't equal. Okay, so then we've got KCNO as well, and the KCNO says that we have 100 grams of that, and in 1 mole of potassium cyanate, it's 81.1 grams, and so that, when I divide that out, is going to give me 1.23 moles. Again, I'm diluting the whole thing to 1 liter, so that's going to be 1.23 molar. Okay? All right. Then, as long as I can find the pKa, I now have everything I need to use in this equation. So I have the pH equals, well, what's the pKa? Well, the pKa is the negative log of the Ka, and the Ka for this was, let's see, it was 3.46 times 10 to the minus 4th. 3.46 times 10 to the minus 4th. Okay, plus the log of the concentration of the base. Well, the concentration of the base comes from this, so that's 1.23 over the concentration of the acid, 1.00. Okay? Notice that this is division and logs, and then I'm going to be adding this together. So you need to do this in two separate chunks to watch your significant figures. So first of all, I'm going to find the pKa, and if I do that, I end up with 3.461. Don't assume that this is necessarily always going to be the same numbers. It was a fluke this time that happened that way, because usually it's not the same number. This, I'm going to divide that out, which obviously it's 1.23. Then you're going to hit the log. And so to three significant figures there, that's going to be 0.0899. Okay. And then I can add those two together, and the pH then is going to be 3.550. I did notice in the book, at least, I do have an older edition of the book, but I did notice in the book that he had a pKa of 3.461, and then when he carried it over to the last part of the problem, all of a sudden he dropped that one off of there. I'm not quite sure why he did that or what happened, but if I maintain that, then I should have this number of significant figures at the end, okay? Now, what you should notice here is that the pH is actually very close to the pKa, okay? And that gives us our first principle, and that's that, if I can get my marker to work here, the pH of a weak acid is actually very close to its pKa. Okay, so that's the first principle. Therefore, if you want a buffer that has a particular pH in it, you need to choose a weak acid whose pKa is close to that desired pH. The more problems you work, what you will notice is that this number over here tends to be very, very small. And so what I add to this, because this is so small, the pKa is going to be close to the pH. And so therefore, the Ka of the weak acid has a whole lot to do with what the pH of the buffer is going to be. So therefore, if you need a buffer of a certain pH, what you need to do is to choose a weak acid whose pKa is close to the desired pH. Okay? So that's a very important concept that you need to make sure you grab a hold of. Again, you can see it mathematically, because this number, this is a ratio. They're normally going to be relatively close to each other because it does set up an equilibrium. So because this number is so small, the pKa and the pH are going to be within the same range. And so that's how you're going to choose how you have what the pH of your buffer is going to be, is by making sure that you choose the appropriate weak acid so it has the right pKa. All right, I think I need to get rid of this now so that we've got room for the other problem that I was going to work with you today. And while we're at it here, let me find another marker so that you don't have so much trouble reading what I'm writing, because my marker is wearing out on me. Okay, so now let's look at example 8.2, and we'll work that problem as well. So now we have an acetate buffer in example 8.2, in which the acetic acid concentration is 0.5 molar and the acetate ion concentration is 0.750 molar. We want to know what the pH is. Then we're going to add hydrochloric acid to see what the new pH is. Okay. So first of all, since we have two questions here, the first thing we have to do is we have to figure out what the pH of the original buffer is. Well, that is a strict application of Henderson-Hasselbalch again. So I'm going to use the exact same equation. So pH is going to be the negative log of the Ka, and he tells us that the Ka for this buffer is 1.8 times 10 to the minus 5. So I'm just going to plug that in that way. And then I need the log of the concentration of the base. And he tells me that the concentration of the base is 0.750. And he tells me that the concentration of the acid is 0.500. Okay, so pretty simple plug and chug equation there. The pH is going to be the negative log of this gives me 4.74. And then the log of 0.75 divided by 0.5 is 0.176. Okay. So again, as you can see, when I add this together to find my final pH, it turns out that my pH is 4.92. And so again, you can see that the pH and the pKa are relatively close to each other. Okay. So again, try to keep that in mind, that the pH of the buffer is going to be very close to the pH of what the pKa is going to be. All right. Now, we have already talked about how that when we add base or we add acid to a buffer, we know that it's not going to change the pH a whole lot. So what's going to happen? Well, he says that we're going to add 30 milliliters of 1 molar hydrochloric acid. Okay, so I have 30 milliliters of 1 molar HCl. So whenever I have a strong acid, that's going to be a complete reaction. Well, what's the hydrochloric acid going to react with? Well, the hydrochloric acid is going to react with the strongest base that's present. And so that's going to be the acetate ion. So that's going to be CH3COO minus. Okay. And then what's that going to make? Well, in a complete reaction, this hydrogen is going to come over here. So I've got CH3COOH. And then I'm going to have a chloride ion. So initially, what kind of concentrations am I looking at? Well, 30 milliliters of 1 molar HCl, that's going to be 0.0300 liters times 1 molar equals 0.0300 moles of HCl, okay? So that's how many moles I have. Remember that when we deal with this, we've got to do moles and not concentrations. So there's going to be a lot of flipping back and forth between these things. So initially, I have 0.0300 moles of hydrochloric acid. How many moles of acetate ion do I have? Well, I knew that my concentration of that was 0.750 molar, but he was also very nice to us, and he told us that we had 1 liter of solution. So since we have 1 liter of solution, the molarity and the number of moles are the same. So that means this is going to be 0.750 moles. Initially, I also am going to have 0.500 moles of the acetic acid, okay? Because that was the initial concentration. I had half molar and I have a liter of it. So I know that I have 0.500 moles. So I should probably put moles on all of these so I don't confuse anybody. And again, that's because I have a liter of solution that these numbers are the same. So after the reaction happens, what am I going to have left over? Well, what's my limiting reagent here? Well, obviously I have a lot less hydrochloric acid than I do of the acetate ion. So after this gets finished, this hydrochloric acid is going to go down to nothing. I'm going to use up 0.03 moles here. So this is going to give me 0.720 moles of the acetate ion. And I'm going to add 0.03 moles to this side So that means this is going to give me 0.530 moles over here. Okay. Now, these are my new concentrations. And notice this is not exactly like the ice table I had before, because I have an initially, and I don't have, I could have put a change in here if I wanted to, but I chose not to do that. But so I'm going to have initial, and then I'm going to have after the reaction is over with, because we're assuming that this reaction is going to go to completion. So now when I calculate this, he was also very, very nice to you, and he told you that even though we added 30 milliliters, that you could neglect that new volume. And so that makes the number of moles the same thing as the molarity, because he said to neglect the volume. And so this is still going to be, since I had a liter of solution, this is still going to be molarity. Okay, so now all that's changed in this equation are these two concentrations here. So my new pH is going to be pH equals the pKa, which I already found was 4.74, plus the log of the concentration of the base, which is 0.720, over the concentration of the acid, which is 0.530. So you can see that this ratio has changed just a little bit. And so now what I have is pH equals 4.74, plus when you type that into your calculator, you get 0.133. And so now my new pH, when I add those together, is going to be a pH of 4.87. So I started out with a pH of 4.92, and even though I added a strong acid, the amount of change of that pH was not very great. Okay, so the problems that I've assigned for you to work today are the ones specifically where you're going to be calculating the pH of the buffer system itself, and then what happens after you add an acid to it, and then we will go into more detail the next time.